This is number 4 off the function table of values, FRQs, non-calculator. Function f and g are differentiable, smooth curve for all real numbers, and g is strictly increasing. The table above gives values of the functions and their first derivatives at selected values of x. The function h is given by h of x equals f of g of x minus 6. So part A says, explain why there must be a value r between 1 and 3 such that h of r is equal to negative 5. So this is no derivatives involved. We just want to look for a location. Can we guarantee a location between given information about the endpoints? And this is going to be applying IVT, which is intermediate value theorem. And IVT says that if one endpoint, if the graph is continuous between the endpoints, and one endpoint sits above the target y value and the other endpoint sits below the target y value, or vice versa, one above, the other below, then the graph has to connect and go through that target y value. Okay, so let's see if we can get that to be true. So let's find h of 1 and h of 3, since those are the endpoints that we're dealing with. So h of 1, we can plug into our h of x function. So it's f of g of 1 minus 6, which is f of 2, because g of 1 is equal to 2, minus 6, which is 9 minus 6, which is 3. So one endpoint is sitting at order pair 1, 3. And the other endpoint, we plug 3 in for our h of x, so it's f of g of 3 minus 6. G of 3, we look at our table of values. G of 3 is equal to 4. So f of 4 minus 6, we go to our table of values again. F of 4 is equal to negative 1. So negative 1 minus 6 is negative 7. So we have two order pairs, two endpoints. One is at order pair 1, 3. The other is at order pair 3, negative 7. And they're telling us that h of x is continuous. Okay. H of x is continuous because f and g are differentiable. So if two functions are differentiable, no matter how much we combine it, our h is going to result in being continuous as well. So I graphed it to help us see a little bit better. If I have an order pair at 1, 3 and another order pair at 3, negative 7, if the graph is going to be connected all the way through, it has to pass through a y value of negative 5, right? Guaranteed. Maybe more than once, but at least once, and that's what IVT, intermediate value theorem, guarantees, that there exists a value such that h of r equals negative 5, because we've shown and proven that we have one endpoint that lies below negative 5 and another endpoint that lies above negative 5, and the graph is going to be connected from one endpoint to the next. For part B, the sentence structure looks the same. We're still starting with the same endpoints, but now we're trying to guarantee a slope. So for part A, we're trying to guarantee a position, and to do that, we're going to use IVT. But if we're trying to guarantee a slope, then that's applying mean value theorem. So mean value theorem says that as long as my function is continuous and differentiable, which it is, then whatever the slope is between the endpoints, that average slope is going to be duplicated somewhere along the curve, and there must be a point, a tangent line to the curve where that exact slope occurs. So let's see if that is true. From our endpoints, we're going to find the order pairs, and then we're going to find the slope. So we're going to use the same order pairs that we did from part A. So we have two order pairs here, 1, 3, and 3, negative 7. So we can just find the slope between the endpoints. So negative 7 minus 3 divided by 3 minus 1. So the slope that we see between the endpoints is negative 10 over 2, which is negative 5. So if there's an average slope of negative 5 between these two endpoints, then there must be a slope of the tangent that is exactly negative 5 somewhere between those two endpoints. And that's what mean value theorem can guarantee us. Okay, for part C, find the value of w prime of 3. We have w of x defined as the definite integral from 1 to g of x of f of t. So if I want to find the derivative of a definite integral, we can apply second theorem. So second theorem says if I want to find the derivative of a definite integral, the nice thing is that the derivative and integral process will kind of undo and cancel each other out. So this f of t function is largely going to remain intact. We just have to make sure we do something with that upper bound. So the result is that the upper bound is going to get plugged into the function because the antiderivative process. And the derivative process is going to have an impact on the p of x, and that's going to result in the times p prime. So let's see if we can use that to apply for this problem here. Here's our w of x in this form. So if I want to find w prime, I'm going to apply second theorem for this process here. So the derivative of the definite integral, g of x gets plugged in for f of t. So it's going to look like this, f of g of x times the upper bound's derivative, so times g prime. So here's our derivative for statement for w prime. So I want to find w prime of 3, replace x with 3, so we get f of g of 3 times g prime of 3. We go to our table of values. G of 3 is equal to 4. G prime of 3, we can do that later. So now we're down to f of 4 times g prime of 3. F of 4, we go to our table of values, is equal to -1. G prime of 3, we go to our table, it's going to be 2. So -1 times 2 is equal to -2. We have g inverse, which is the inverse of g. Write an equation for the line tangent to the graph of y equals inverse of g at x equals 2. So we're dealing with x equals 2 for our inverse function. Right? This x equals 2 is for this inverse function, which means that for the original g function, the 2 must be the y value. Right? So that means if I'm trying to locate my order pair for my inverse function, and my order pair starts at x equals 2 for my inverse, the relationship is that if the inverse has an x value of 2, that means the original function has a y value of 2. So let's see, is there anything that will give us a y value of 2 for our g of x function? And we're able to spot it here. We have an order pair of 1, 2 that sits on the graph of g of x. So if there's an order pair that's 1, 2, then on the inverse there must be an order pair that is 2, 1. And we already know and given that the x value for the inverse is going to be 2. So that's our order pair that we're going to be working with, order pair 2, 1. And we can also build a relationship between a function and its inverse's slope at their corresponding points. So now that we know the corresponding points between g and g inverse, we know that if we can figure out the g graph, the slope of the g graph at 1, which go to our table of values, g prime of 1 is equal to 5. So if the slope of the g graph at 1 is 5, then the slope of the g inverse at 2 is always going to be reciprocal. So these two numbers numerically are going to be related. They're always going to be inverses or reciprocals of each other. So we have information about the slope that we want. We also have the order pair information. And once we've gathered this, we can put into point slope form. Y minus 1 is equal to slope 1/5 times x minus 2.